My institute manages the Polish Polar Station, located in Svalbard, in Spitsbergen. And there we have glaciers, just nearby the station. The closest one is just 2 kilometers from the station. It's called Hansbren. And in the surroundings, there are many landforms. And that's something that I would like to show you today. These landforms connected with glaciers. So the topic of my lesson is how glaciers shape the Earth's surface. There are many landforms and actually many definitions, and I guess you have them in your books, so I'm not gonna give you exact definitions of them. I just want to show you how they look like. I know it's almost the end of the academic year, so vacations are coming and no one wants to see definitions. So this lesson is just to show you the landforms, how they look like. I promise not to give definitions, but the shortest one is of a glacier. It's a mass of ice that continuously moves from higher to lower ground. In other words, it can be said that a glacier can be described as a frozen river of ice. But rivers have liquid form of water. Glaciers have solid form, and actually solid form shouldn't float, shouldn't go as river, but actually glaciers behave as rivers, but they just move slowly. It can be up to hundreds of meters per year or dozens of meters per year, but in some cases, in case of bigger glaciers, it can be even dozens of meters per day. Usually, I guess you can observe glaciers on pictures, and actually if you'll go to the field, you will also see the glacier that looks motionless. Their mass movement is really powerful. It shapes the Earth's surface, but with your bare eye, when you're there, you cannot see the movement. It takes time. It's not as fast as floating river. So there's no flow of ice in such definition as in the case of rivers. But if you'll set up cameras, if you'll take pictures, for example, once in 3 hours, you will see the glacier movement. And this glacial movement, together with all the transported material, destroyed the bedrock which is underneath or in front of the glacier. Glaciers erode slopes of valleys. They reshape existing landforms because they just push everything and lay down the materials. They move and accumulate materials on the sides, at the bottom of the glacier, and in the forehead of it. Just to show you how it can look, I will just show you a short time-lapse video. It's from a movie called Chasing Ice. That's a pretty good movie. I recommend it to watch. But just to show you how the glacier can move, that's Columbia Glacier in Alaska, and time-lapse pictures taken in 3 years, in 3 months. Yeah, so if you're there, you won't see such movement, but if you will have observations for longer time, you can observe how the glacier floats down. And this flow of the glacier can reach up to hundreds of meters and even more during a year. And what can be observed on these pictures, in case of Columbia, you can see the retreat of a glacier. So the front of the glacier moves back. And as you can see, it's pretty far distance in this case. That's for the scale. Yeah, let's go back to the presentation. So, as I said, on the pictures and in the field, glaciers seem motionless. But once you have observations for longer time, you can observe them moving down, floating down. And glaciers, it is said that they can be called nature's bulldozers. Why? Because when they move, they do such things as bulldozers. For example, they shape land in three ways. They pick up material. It's called erosion. There are processes of freezing and thawing, so the weathering underneath the glacier. When the water freezes underneath it and the glacier moves, it plucks the material and the material is abrased, so it's called abrasion. And another way is transportation. So the glacier picks up materials, it transports materials, and then it deposits the materials. And those deposited materials can be observed as different landforms. But where can we observe glaciers? They exist in places where seasonal snow accumulation is higher than seasonal melting, called ablation. And the main factors for glaciers to exist are climatic conditions, such as air temperature and precipitation. So the air temperature has to be low. The precipitation has to appear as snow, so there will be snow accumulation. If this snow will stay from previous winter throughout the summer for the next year, then you have conditions where the glacier can maybe appear, but it won't appear next year. It takes longer time. It depends on climatic conditions, weather, so there are seasonal different meteorological elements that influence glaciers. For example, if the summer will be too hot, the snow from previous year won't stay there, it will melt. That means that not only winter influences glaciers, but also summertime. And of course, there's also geomorphology. As you can see on this picture, there are glaciers, but only in places where the snow could accumulate. So if the slope was too steep, the snow didn't stay there. And exposure. If the slope is facing south in the northern hemisphere, it will have more sun, so it can be warmer, the snow can melt. The slopes that face north in the northern hemisphere will have less sun or not at all, so the sun won't melt this snow. Extent of the sites where the snow can accumulate are determined by snow line. This snow line is called equilibrium line altitude, ELA. That's the height above which the snow doesn't melt during summer. So the snow and ice cover stay there throughout the year. Snow and ice from direct snowfall, also from blown snow, and avalanches that can come from surrounding mountains above the glacier. These are collectively termed accumulation. So if you add snow to the glacier, it's called accumulation. The opposite situation is called ablation. So the process of wastage of snow or ice by melting, sublimation, or calving. On this picture, you can see the accumulation zone in the upper part of the glacier. In the lower part, there is ablation zone. Because ELA determines where the snow will stay throughout the year, but the glacier moves down. As it's pushed from the layers above, there's more and more snow every year. So the snow from the top pushes the underlying layers of snow, which are squeezed, and then the glacier ice can appear, and then the glacier will float down. If it flows down, it's lower, so it reaches ablation zone, where it's below equilibrium line altitude, and that means that below it, the snow won't stay there for the whole year. It will melt during summer. So during winter, there's accumulation on whole glacier usually, and during summer, in the ablation zone, in the accumulation, there's also ablation, but the snow from previous year usually will stay. That's why it's called accumulation zone. But equilibrium line altitude, it's the height, as you can see here is the red line. It can change depending on weather conditions, on meteorological conditions. It can move up and down depending on years. So if you have warmer summer, the ELA will go higher up. More glacial will be in the ablation zone. If it's cold, the ELA will move down, it will be lower, so the accumulation zone will be bigger than ablation zone. If the amount of snow that accumulates during winter is larger than the amount of melted snow, the mass balance is positive. So ELA will be lower, mass balance will be positive, and the glacier will increase in volume, so it will grow bigger. On the other hand, if melting of snow and ice during summer is larger than supply of snow in winter, the mass balance will be negative, and the glacier volume will decrease. So the glacier will shrink. And here are examples of glacial budget if accumulation is lower than ablation. So the ablation will be higher, the mass balance will be negative. If accumulation is higher, the mass balance is positive. And that's it. That's how the glaciers behave. The more snow accumulates, the bigger the glacier can grow. Recent glaciation looks like presented on this map. So there are two huge ice sheets, Antarctica and Greenland ice sheet. And there are also mountain glaciers on each continent, except of Australia, but there are glaciers in, for example, New Zealand nearby. And the average height of ELA, of the snow line, varies with latitude. Near the poles, it's around 0 meters above mean sea level. In polar zones, it can reach up to 1,000 meters, but it's between 200 and 1,000 meters. In mid-latitude, such as in Europe, it can be between 800 to 3,200 meters above mean sea level. In tropics, the ELA is between 5,000 and 6,000 meters above mean sea level. In the equator zone, it's between 4,500 to 5,000 meters above mean sea level because of higher precipitation. So if the heights, if the altitude in these places is above these heights, above these levels, the glaciers can appear. And there are glaciers in high mountains around the world. As you can see, here I just draw the line of ELA, equilibrium line altitude. It can vary, so it doesn't mean that it goes as mentioned here. It's never same height, never the same altitude. In different years, it goes in different way, and also for different valleys, it can look differently. But how to transform the snowflake, which is really light, into glacier ice? The snow crystallizes from atmospheric moisture, then it accumulates on surface of the earth when it falls as snowfall. When it's accumulated, snow crystals become more and more compacted, so it appears as granular snow. The air is forced out of a pack, the density increases, then the firn can appear. If the layers above will squeeze and push down, the glacier ice can be produced. And in this table, you can see the density of snow and ice, the density in given volume. For fresh snow, it's around 100 kilograms per cubic meter. In case of settled snow or wind-packed snow, the density is higher, so it can be up to 400 kilograms per cubic meter. In case of firn, it's between 400 to 800 kilograms per cubic meter, and glacier ice is almost as dense as water. In case of water, the cubic meter will be 1 ton, 1,000 kilograms. The glacier ice is between 830 to 917, or a little more in density. So the density of ice is pretty high. There's no that much air as in case of fresh snowflakes. Conversion of snow to glacier ice takes usually many years. When enough ice is accumulated, the ice begins to move downslope under its weight and pressure of overlying snow and ice. So the glacier ice starts to move and flow down the valley. So as you can see on this picture, the movement can be seen as these crevices appear. It moves down. What's underneath, it will produce these crevices because the glacier ice can crack in such places. Here are examples of two glaciers in Alaska. And when glacier ice moves down the slope, it pushes the material and it transports the material inside the glacier. On its sides, in this case, you can see the left side of the glacier. The material is also pushed underneath the glacier. Inside the glacier, it's never pure ice because this material is transported inside as well. So it will go inside the glacier, it will be squeezed and transported down. And also on top of the glacier, there can be huge erodics, huge rocks that are transported with it. For the scale, there's my colleague underneath this rock on top of the glacier. And the material, it can be a lot of it, as in case of Tasman Glacier in New Zealand. You can see how much material can be transported, and this material can even isolate the glacier which is under this material. In case of this glacier, there's lots of rocks that now prevent faster melting of a glacier because there is insulation of these rocks above the glacier. But it's still not enough to prevent melting of it. Glaciers can terminate on land, as in this case, and they can also terminate in sea. In the contact between water and glacier, there is a process of calving, so the breakaway of ice blocks or icebergs. And that's natural process of calving. Because glacier takes the material, it transports the material, there are different erosional glacial landforms. So the material, when it's taken away, these landforms appear. So such as glacial scratches, glacial striations, glacial balls, and troughs. Just to show you examples. Striations. When the glacier was moving, it was further to the right side of the picture. It was scratching the rock that was under the glacier. Now when it retreated, you can see those striations on top of these rocks. And these striations and scratches, they go as the glacier was moving. So in this case, from the left to the right. And also they can be seen here on the rocks. When the glacial scratches the land underneath, the scratches can be seen when it retreats. In case of balls and troughs, if the material is not that hard, it can be pushed out. So when the glacier moves, you can see such balls as here. There are also transformed erosional landforms, such as cirques, rock steps, moutons, nunataks, fjords, fjelds, also U-shaped valleys and hanging valleys. Examples: cirques. They have amphitheater shape. There are also rock steps. You can see them. These were where the glacier were connecting with each other. The one was above another one. So you can see the rock steps. The glacier above was floating into bigger one. In the past, And I mentioned about this amphitheater-like valley heads, cirques. These are examples from Svalbard. Moutains. In case of moutains, you can see those from the previous picture. These are the same. The glacier is on the left, and they are, as you can see, more flat because they survived when the glacier was moving. These are strong rocks, and now they can be observed as moutains. Nunataks, these are mountains surrounded by glaciers, so higher than a glacier. There are nunataks inside huge glaciers, especially in Antarctica, but also in Svalbard, as you can see. When the glacier moves down the valley, it pushes out all the material. So when there was V-shaped valley produced by a river, the glacier will just push the material and it will produce the U-shaped valley. So that's U-shape, as can be seen on this picture and also on this one. So these are valleys that were reshaped by glaciers. There are also fjells, the flat mountains, and fjords. I would like to show you how the formation of fjords can look like. So when the glacier mass balance is positive, so it's colder, the glacier grows, it expands, and it floats down the valley. Of course, it takes many years, but if it's cold enough, it can even reach the sea. So there are processes of calving. And then when the climate is warmer, the glacier will shrink. But if the material was pushed away, it was taken away, under the glacier when it retreats, there can be valley that can be flooded by the sea. And this is how the fjords were produced. So that's just to show you how the fjords appear. There are also depositional glacial landforms, such as terminal moraine in front of the glacier, lateral moraines, medial moraines, ground moraines, kettles, cenders, glacial fluvial cones, cams, eskers, and drumlins. So in case of terminal moraine, that's the material that was pushed in front of the glacier. When the glacier retreats, so the climate is warmer and glacier doesn't grow, it shrinks, it goes back, it melts. The material that is laid down by the glacier and is pushed by it stays as moraines. In case of terminal moraine, it was in the front. There are lateral moraines on sides of the glacier. And there's also ground moraine. The material that was on top, inside, and underneath the glacier stays there as ground moraine. All waters that float from the glacier transport also the sediments, and these sediments are laid down in front of the glacier and they produce cenders. Here is an example of material deposited by glaciers, so as I mentioned, moraine. Oh yeah, just for giving the scale, look at this area here. Here I zoom in just to show you my colleague for the scale. So it can be lots of rocks and different sediments laid down by glacier. And here are different moraines on sides. If there are two glacier tongues, because there can be, for example, two cirques, and on the way down those two tongues of glacier can meet. Between them there will be medial moraine. In case of glaciers that terminate on land, those landforms, such as moraines, can be visible. But if glacier terminates in sea, they are not visible. But if you'll check the bathymetry, as my colleagues did in front of Hans Glacier, you can see what's under the sea. So what's at the bottom of the fjord. And here you can also see the materials that were deposited. So moraines are visible, even though they're not visible from top, only that's the bottom of the sea. So this bathymetric map also shows all these materials, all these landforms. And my colleagues produced this geomorphological map, so you can see also terminal moraine. It's not visible from above the water, but under the water there are also such landforms. So if you have bathymetry of given fjord, you can also say what was the extent of the glacier in the past. Of course, when the glacier melts, if it's possible for the lakes to appear, there will be glacial lakes in front of the retreating glacier. There can be also glacial fluvial cones, such as in this case. So that's on the slope. There are also eskers and cams. And when the glacier retreats, the fresh landforms can be visible in such landscape. But with the time, these landforms are getting flat because of the erosion. So after a long time, you won't see those. So the fresh landscape, when the glacier retreats, it looks like that. But after a long period, it will be more flat. There will be lakes, as in case of northern Poland, for example. But the best to see how these landforms were produced is going to the glacier, seeing the landforms that were produced, and then you can have comparison. Yeah, such as in this case. Recently, there are advances in technology. So we are able to reach different remote places of Earth. And this allows us better recognition of polar and mountain areas where glaciers form. And the science that deals with the study of glaciers is called glaciology. Study of the landforms is called geomorphology. As glaciers retreat, there's less and less work for glaciologists, although it's more interesting for them to have glaciers. But when they retreat, there's more work for geomorphologists, for mapping landforms. So as you can see on this picture, above is a picture taken in 1985, below is picture from this decade. I just took it a few years ago. You can see the extent of Horby Glacier. That's also a glacier in Svalbard. When it was in that point, the mass balance was more positive than recently. So the glaciologists could get to the glacier. It was closer to get there. But now they have to go further. If they go further to the glacier, geomorphologists can map the landforms in front of it. The current global trend of glacial mass balance is negative, so most glaciers around the world retreat. We observe climate warming, and it's been observed since 20th century. It's ongoing process in the 21st century. That means that more energy from the atmosphere melts the glaciers. And there's also warmer ocean waters that increase the intensity of calving. The negative mass balance is observed on mountain glaciers and also on ice caps, and recently also in the Antarctic ice sheets and also in Greenland. There's lots of articles about that. I won't go into details of that, but you can just hear in the media that the mass balance is negative. The global warming, that's something that's happening. it's hard to stop it. There are different ideas how to stop melting of glaciers, but actually most ideas are, we're not able to make them. So the Earth system is warming, and now we observe the retreat of the glaciers. When they retreat, there's more and more landforms that can be visible now. Before, and when it was colder, they were under the glacier or in front of it. Now, when the glaciers retreat, they appear on the Earth's surface. Here is an example of some old picture from 1895 and picture that I took last year. That's in New Zealand. So you can see what was the extent of the glaciers more than 100 years ago and where are they now. And also these landforms. You can see on the picture below that the moraine that was in front of the glacier was pretty big. There was ice under this moraine. Recently, the area is almost flat. There is this lake, there is a river that goes out from the glacier and from this lake, and the material deposited by a glacier is floating away. The sediments are taken away, and the landforms are flattening. So that was just to show you how it looks. There are lots of different glaciers, lots of pictures from previous times, what was the extent, and recently to reach the glaciers, in some cases, when it used to be a glacier ice, now it's lake, so you can just reach the glacier by boat. There are two to-go messages that I would like to share with you. Glaciers are sensitive indicators of climate change. They constantly grow and shrink in response to changes in temperature, snowfall, and also other factors influence glaciers. What else? Glaciers have tremendous power to drastically transform landscapes over relatively short periods of time. When they move, they will transform everything what they meet on their way. Here is a list of some references. There's also definitions in our Polarpedia as part of EDU-ARCTIC. If you have any questions, I'll be more than happy to answer them. Thank you for your attention.